Assalamu alaikum wa rahmatullahi wa barakatuh. Friends, welcome back to my channel. In this session we will see how we can troubleshoot our 384 series ICs which have 3842, 3843, 3844, 3845. Either it is 1842, 2842, 3842. Similarly 1843, 2843, 3843 and 1844, 2844, 3844, 1845, 2845, 3845. This is a complete family. It is current mod SMPS controller. The circuit of all this family will remain approximately same. There will be very minor changes, and in this video we will cover most of the common faults in this circuit design. When we say this is a family, these ICs differ from voltage value from one to other and duty cycle. The frequency and drive, all other features will remain same, just only frequency and duty cycle utilization will differ to one to each other. So let's start. This is a sample circuit. This is not exactly the same circuit designed for this power supply. If you have any power supply, either it is 384 series, any type of power supply, just only locate the part number for that IC and go to Google. Download its datasheet or its application notes. You can search through PDF format files and you can find approximately, we can say, from 90% to 99% the same circuit. Sometime this circuit is 12 volt 4 ampere. This is sample circuit. It is available in the circuit diagram. Typical application design example. It is an example circuit. So we can take a good image, good idea about the IC and how it will work in the circuit. All the functions are most of the time explained in its data sheet. If the explanation is not available there, by seeing the circuit we can take idea how this circuit will work. Here it have input circuit, that is line input, line and neutral. These two wires, these lines will reach to some current protection, that is fuse. This line is reaching here, and after fuse both lines are reaching here at this point. What is here? Here is a dual line filter. This line will go here, enter in the fuse, and after fuse it will come here, and this line will come here. These will pass through this dual line filter. Then we can see this line is reaching here and this line is entering here in one component. What is that? That is Inrush protection circuit, NTC, negative temperature coefficient resistance. It will protect the inrush current. So when the capacitor is empty, it will take a heavy surge. It will try to draw full amount of current from the line, which can damage the circuit. For that purpose, this NTC will limit the current. Then there is over voltage protection, surge arrestor, that is connected in both lines. MOV or surge arrestor. After that there are capacitors. Here we have another surge arrestor, then we have capacitor set, class Y, class X capacitors, and then we have this accelerated capacitor, and we have this inductor here, dual line filter, then we have another dual line filter for energy storage. Then these line and neutral voltage are reaching to bridge rectifier. Then these voltage will reach here at this capacitor, that is here. Here we have bridge rectifier. These voltage are reaching here and these voltage are reaching here. Then these will pass here, it will pass here to the inductor. After inductor, here we have inductor. Then these voltage will reach at this bridge rectifier. Then here we have negative, here we have positive voltage. And if we check here we have winding. This is MOSFET. Until now, the first problem that if the fuse is blowing, we have problem from this side to back side. What is there? Look from this point. If the MOSFET is short circuit, if it have internal short circuit, what will happen? This negative voltage will pass directly to the positive terminal, and this transformer winding, it don't have too much resistance. At that time, it will give a easiest path to all the voltage and it will make short circuit. Okay, this is one condition for the fuse burning out. Second thing, if this capacitor is short circuit, it will make a discharge from this point to this side and it will reflect back to line and neutral. If these components are bad, bridge rectifier is bad, at that time it will give easiest path. For example, if any diode out of 4 diodes that are within this bridge molded pack, if any diode will damage, it will make short circuit and it will be a reason to burn out this fuse. In series line, we have dual line filters. If any one filter is open, it will not allow to pass the voltage and we will not receive voltage here. It is already a piece of wire, it will not make a short circuit. Any component connected between the parallel line, if that is short circuit, fuse will burn out. Class X capacitor, Class Y capacitors, surge arrestor, second MOV, that is here. If these components are short circuit, fuse will burn out. If NTC is damaged, it will make open circuit. When it will become overheat, its plate will separate it. So we can say we have 1, 2, 3, 4, 5, 6, 7, 8. If we check continuity between these two terminals and the capacitor negative and positive terminal, if we find continuity there, then there is a reason for short circuit. That first check the DC voltage here at capacitor to confirm short circuit. Okay, there are no voltage. Check continuity here. If we have continuity here, there is a beep. At that time, there is a short circuit in the line. Any one component. Now, if we test short circuit here, if our MOSFET is short circuit, okay, let me correct practically. If our MOSFET is short circuit, from these 2 points, drain to source, it will give continuity. Okay, if we connect at these 2 terminals, if I connect multimeter at these 2 input terminals, any component here that is in parallel line, for example, we have this capacitor here. If it is short circuit, class X capacitor, it will give indication. Okay, if we have this surge arrestor, if it is short circuit, we will receive continuity. Fuse we can test directly. How we can test NTC? Set in resistance mode. It will give resistance. We can heat it up and we can check either it is functioning or no. If you want to test the function of this NTC, just heat up we can see the resistance is increasing. This NTC is working. After that, if we verify all this cold testing and we connect power, we apply power, then the fuse burns again. That means there is another thing that is here. That is PWM driver IC. This MOSFET, and behind this MOSFET we have this IC. If this IC is bad, if this IC is damaged, it will directly turn on this MOSFET, and when this MOSFET will receive signal, the MOSFET is good, but the false signal will switch this MOSFET. If this IC is good, it must block the voltage. It will allow this MOSFET to turn on for the specified time, that is a pulse signal. We will verify on the oscilloscope and multimeter. So it will allow for the specified time to turn on this MOSFET to allow the current. If it is permanently on, that means there is something wrong at that time. The MOSFET will allow full current to flow and it will cause to damage this fuse. To verify it, remove the MOSFET, apply voltage, line voltage here, check voltage at DC capacitor and use series lamp. DC voltage, always take care for the safety. If you don't have good practical experience, never try to repair it. When we apply voltage to this power supply, if the lamp will glow for a while and then it becomes to normal state, that means the circuit is good. It will just only take a surge current for powering on. Yes, now it is on. Check DC voltage at the main DC capacitor. It is 318 volt. That's good. And these voltage must be stable. These voltage must be stable. If fuse is burning again and again, remove this MOSFET. If the lamp glows fully, when we are using series lamp, at that time the fuse will not burn out. If the lamp indicates full indication, I will make a short circuit here between drain to source. If the MOSFET is short circuit, the lamp will glow full. That means the MOSFET is short circuit or any other component. If there is this capacitor is short circuit, if anything here is short circuit, for example this bridge rectifier is short circuit. If the bridge rectifier is short circuit, we will find the full light in the lamp. When the circuit is good, it will not give full light. We discussed if the fuse burns again and again until here. Now I will remove this MOSFET. Now I remove the MOSFET. What will happen now? This time we will see voltage here at this capacitor, at main DC capacitor that is here. But now the MOSFET is not present, so no current will flow in the transformer. What will happen? We will receive voltage at this VCC capacitor that is connected at pin number 7. Pin number 7, pin number 6, these have clamper diodes. Most of the time these are 18 volt clamper diodes for the protection of the circuit. In some circuits these diodes are available, in some circuits these will not available. No problem. Okay, we have startup resistor here. Initially when we apply power, This startup resistor will apply voltage to VCC capacitor, and when this IC will reach at 16 volt, it will start switching. It will start switching. At that time, we will find a drive signal at the gate pin, that is here. If we receive gate pulse, that means the circuit is good. If we don't receive gate pulse, that means we have problem in startup circuit, that is here. Sometimes this capacitor is bad, sometimes this resistor is open, and sometimes this IC is bad. Any one component failure will cause to missing of drive signal. Let's check it. To test the drive signal, most of the time I use this UC384x clamp meter. It is very good in frequency response. By this multimeter, it don't have a very good frequency response for the high frequencies, especially for the PWM signals. Sometime it works, sometime it don't work. I will set to Hertz. I will connect black lead to the ground terminal, that is common point, and I will connect this lead, red lead, to the gate pin. It is giving 17 kilohertz, 18 kilohertz, 17 kilohertz. This time the IC is in reboot mode. Now if I check the voltage here, DC voltage at pin number 7 and ground, we can see the voltage are fluctuating. Why? Because this resistance is high value resistance, and it will allow just only 1 milliampere charging current to this capacitor. When it will reach at specific limit 16 volt, that is upper threshold for turning on, when it will turn on, at that time this IC will start to take 17 milliampere. This source is providing 1 milliampere, and here we are consuming 17 milliampere, so that is the reason this capacitor will start to discharge. When it will reach at lower limit, this IC will turn off internally. That means this IC is working nicely. Now when this IC will turn off, it will wait until the voltage will reach again up to upper limit. When it will reach up to upper limit, it will start to switch again, and we will find the signal again here. So that is the reason we are taking ground and gate pin 17 kilohertz, 17.9 kilohertz. And if I check with this multimeter, DC voltage at pin number 7, we can see it is fluctuating. It is not fluctuating. Basically, it is indicating that IC is in restart mode. IC is in reboot mode. Now ground and pin number, ground and this drive pin, we can see it is trying to measure some voltage, but it cannot measure because that is drive signal. If I check with the AC voltage, it will give around 2.2 volt, 3 volt, and it is giving approximately 6 kilohertz, 7 kilohertz signal in the secondary display. And if I move to millivolt range, AC millivolt range, and here I will use Hertz function, I will try to measure the volt frequency. So this multimeter don't have a good frequency response. At that time it is measuring 4.7 kilohertz. If I reverse the lead to check negative duty cycle, it is giving 14 kilohertz. That is not a satisfied reading. I will use oscilloscope for that purpose. We need to connect ground signal. When you are working on the board, always remove power. For soldering, desoldering and all other work. Now I will test the signal at gate pin. We can see the signal shape I will set auto set. These are bursts. The IC is making burst. How it will work? Let's monitor this burst, one burst. When the IC will start switching, it will use its duty cycle to receive feedback, and it will continue. When the capacitor will discharge, because it is not receiving VCC voltage, IC will turn off. When it will turn off, it will wait until the capacitor is charged again by the startup resistor. Then it will start switching and feedback will not available, capacitor will discharge and it will charge again. The IC is switching now in form of packets. This time the IC is using 25 packets in 1 second. How we can say 25 packets? 25 packets of 73 kilohertz, and if we check the condition of pin number 6, that is here, now we can see the capacitor charging time, discharging time. It is charging and discharging at the same rate, which is here. The IC will switch and it will wait until the feedback, and it will reach in UV under voltage lockout condition, so that the IC will turn off. When it will turn off, the capacitor will charge again. The capacitor will charge again. So that the capacitor will charge, and in this period the IC will work. When it will work, at that time it will reach in UV under voltage lockout. When it will reach in under voltage lockout, it will turn off. Then it will allow to charge the capacitor again. So this is the capacitor charging, discharging at VCC pin. So IC is switching in form of packets. Each packet, it has 73 kilohertz switching frequency, and it will switch the same 25 hertz, 25 packets in 1 second. This will differ circuit from circuit to circuit, from one circuit to other circuit. When the feedback is missing, it will switch at its rated frequency, and then it will wait until the capacitor is charged again. Because there is no MOSFET, this time it is not switching. Let's check with multimeter. It is measuring 17.5 kilohertz. Why? Because it is taking 73 kilohertz, and then these packets are divided, so it will take the mean value, the center value. So in reboot mode we will see the lower frequency, less frequency on this multimeter. It will give an idea that it is in reboot mode. When we see on the oscilloscope, we see 25 packets of 73 kilohertz in 1 second. Now we will connect this MOSFET. When this MOSFET will present, and then we will see the signal here. This time I connected the MOSFET, and now if I will check the voltage here at DC capacitor, that is pin number 7, it is 14.8 volt. This time these voltages are stable. Why? When we connected this MOSFET, what happened? This IC, before this, it was rebooting. It was seeking for the feedback. It was seeking for these voltage that are from the bias winding. When this IC will start switching, it will allow to flow the current from negative terminal, that is here, to the winding, to the capacitor positive terminal. It will allow pulses. These pulses will make magnetic field in this primary, and that magnetic field will cause to induce the voltage in the secondaries. We have two secondaries here, one in the output section, second in the auxiliary winding, that is bias winding or VCC winding. From the VCC winding, now we are taking this voltage to the biasing diode rectifier. It will allow voltage to charge this capacitor so that it will compensate the requirement of this IC, because here we are taking just only 1 milliampere. If this diode is bad, this resistor is open, we have ground disconnection here, or we have this capacitor bad, this IC will fluctuate. This IC will go in a reboot mode, because if this capacitor is not holding the charge, even these voltage are providing the charge, it will make ripples here at this pin. When the voltage will drop from threshold, this IC will turn off. Set multimeter to frequency, and now we will check the frequency. What is the frequency right now? When you are going to test the frequency, very carefully connect multimeter probe very carefully at the gate pin. It is giving 73.8 kilohertz. This time we have switching frequency 73.7 kilohertz, 73.8 kilohertz. Check the duty cycle. It is 12.4%. Why? Because it is not driving any load. Now let's connect oscilloscope. I will connect here at this point. Yes, it is exactly 73.5, 73.7 kilohertz. And this clamp meter, it gives the correct reading 73 kilohertz. That's nice. And if we check duty cycle, it is 11.7%. You can check duty cycle, you can check the voltage. The second symptom here, that there is switching, how we can verify? Check voltage at this VCC capacitor, that is this one. DC voltage at pin number 7 of this IC. UC384x pin number 7. It is 14.5 volt, and we can verify the voltage at pin number 8. Pin number 8 and ground, 5 volt reference. These voltage must be available if the IC is good and auxiliary winding is good, bias section is good. At that time this IC must have 5 volt, otherwise if don't have 5 volt it will not switch. This is one condition. Now how we can verify the switching from the MOSFET? DC voltage, check voltage at ground pin and the capacitor, 317 volt. It is 317. Now check the voltage at the MOSFET. It is 375 volt. Voltage at capacitor 317, and voltage at drain of the MOSFET 375, 372. That means there is switching. How we can say there is switching? When this MOSFET will switch, at that time it will allow to pass the current from the winding. If it will pass the current from the winding, the voltage will induce in the secondary and auxiliary winding. At that time there is a reverse magnetic field caused by the off duty time. When the IC will turn off at that time, this collapsing magnetic field will create reverse magnetic field that will in series of this capacitor. So it will create stress on this MOSFET. So that is the reason we are receiving 370 volt here. Here 313, 314 volt, and here we are receiving stress. So that is indicating that we have switching in the MOSFET. If this snubber circuit, it will not work, it is short circuit, it will not give a good reading. At that time we will not take good voltage in the output side. If there is no stress, if there are no elevated voltage at drain of the MOSFET, that means there is no switching. If the drive signal is not present, that means we have something wrong here or something wrong here. What are the possibilities? We have one clamper diode here. If it is present, check it. It is 18 volt most of the time, or sometime it is Schottky diode with 18 volt blocking voltage. Then we have this resistor, and sometime in parallel to this resistor there is a diode 1N4148 that is connected in this condition in parallel to this resistance. And sometimes we have 20 kilo ohm. Here it is using bleeder resistor 10 kilo ohm. Sometimes here is a 20 kilo ohm resistor. So we need to verify this resistor here. If any one component is bad, MOSFET is bad, then there is a resistor here, that is current sense resistor, that is connected between ground and the source pin of the MOSFET, that is connected at this point. This is negative terminal is reaching here. We have resistor here, that is here inside. If this resistor is open, at that time it will not allow to pass any current from the winding, so that the circuit will not start. What are the checkpoints now? Check the voltage at 7 number pin, 15 volt, 13 volt, whatsoever, and 5 volt must be present here. In some circuits there are two transistors connected to pin number 1 and pin number 4 to adjust the frequency. If these transistors are there, check these transistors. Then we have RTCT, pin number 4. We can also verify the frequency here at pin number 4. The same 73 kHz frequency is there. These ramp signals, these must be present at pin number 4. If this frequency is present, at that time it will make PWM signal here. So it is 73.55 kHz signal that is available. So we need to verify these signals. Okay, the next we have feedback circuit. When it will apply voltage to the winding, we will receive output voltage here. When these voltage are here at output terminal, these must be stable. Here are now some conditions. What are that? The first condition, that this rectifier, it must rectify the voltage. If this rectifier is short circuit, now the first condition, if this rectifier is short circuit, what it will do at that time, it will apply AC voltage to this capacitor, because after passing these voltage from the winding, these voltage are in this condition. At that time this capacitor will create a short circuit, so no voltage will there will be very little voltage in millivolts at the output terminal. And the condition there, that this capacitor will fluctuate, the voltage will vary here, and pin number 7 of this IC will also vary. That will indicate that there is short circuit. Condition, low voltage here, very low voltage here, and we can also check the voltage across the rectifier. Let's check it. DC voltage, we are checking voltage across this rectifier. If we have 24.95 volt, that means this rectifier is working good. This rectifier is blocking reverse voltage, this negative peak. That means our circuit is working. In any case, if this rectifier is short circuit, at that time, here we have switching. We check that there is a stress on the MOSFET. If the stress is available and the IC is fluctuating, at that time this circuit will not allow to build the voltage here. At that time we need to verify this rectifier, this capacitor, that is after this rectifier. If this capacitor is short circuit internally, rectifier is good, but it is making short circuit, it will be a reason to make fluctuation, because this fluctuation is basic key for the regulation. Now these voltage, positive voltage and the return line, these voltage are reaching at this voltage divider network, this 9.5 kilo ohm and 2.49 kilo ohm. These will divide these 12 volt here. When we will receive exactly 12 volt, at that time this voltage divider network will provide 2.495 volt, 2.5 volt here, and it will allow cathode current to drive this LED in the optocoupler. This current limit resistor, it will limit the current to drive this optocoupler, and this transistor will switch. When it will switch, at that time it will give a signal to feedback pin that the voltage are reached there. At that time this IC will limit its duty cycle, DC voltage. And if we check voltage here across this optocoupler, it is 1.74 volt, and if we check voltage here, it is around 2.5 volt. When it is around 2.5 volt, that means it is giving feedback. In some conditions this optocoupler is bad, and in some conditions our TL431, that is bad. That is here. If we check between ground and this pin, it is taking 2.48 volt. It is pin number 1. When the required voltage are present at the output terminal, and that voltage divider network, that is here inside this circuit, and in your circuit this will be a resistor combination here. If there is no resistor combination, sometime there is just only one Zener diode in series of this network that will do exactly the same job. We must find 1.07 volt, 1.02 volt, depending on the LED current. At that time this IC will regulate the voltage, it will adjust its duty cycle. If we don't have this TL431, this is our positive terminal and this is our return terminal. Sometime in the positive terminal there is a Zener that is connected here, and in series optocoupler, and here is a resistor connected for current limit. And it is to control the PWM IC. If we need 12 volt, most of the time 12 volt Zener is used here. At 12 volt it will allow the current, Zener current. When the Zener current will flow here, at that time this optocoupler will switch and it will provide regulation. When the voltage will drop, this Zener current will drop and it will change the conduction of this optocoupler. It will control the voltage. Another fault condition here, this was the short circuit. If any component, rectifier is open, track is break, winding is open, winding does not open, sometime it is disconnected from the board. We have bad soldering here, dry joints. If we have dry joint, it will not allow to pass the voltage. At that time the circuit will fluctuate in the primary side and we will not receive voltage here. At that time we will not receive any feedback. At that time IC will use full duty cycle to take feedback if any component is bad here. optocoupler is bad, any component, resistor is damaged, for example track is broken, whatsoever, any condition that this 1 volt not available at this point, reason being here we have open circuit, here we have something problem in this circuit, this IC will switch at full duty cycle. At that time this winding will provide voltage here. It will allow to charge at full level because full magnetic field is here. It will make more voltage here. It will go in over voltage protection mode. Pin number 7 will increase. When it will increase, IC will turn off. It will wait until the voltage will return back at pin number 7 less than its lower threshold. Then it will start to charge from this resistor and it will restart again. So this is one condition. The second condition, if this circuit is good, we have problem here. At that time we will receive more voltage than the rated voltage. For example, this supply is 12 volt. At that time maybe we will receive 30 volt, 25 volt. This circuit have problem. This circuit is good. Duty cycle is used full, so that IC needs feedback to pin number 2. When it will not receive feedback at pin number 2, in that condition we have more voltage with fluctuation, check this circuit. If we have no voltage at all, check this circuit. If we have very low voltage, now here are 3 conditions. Very low voltage, short circuit. No voltage, open circuit. High voltage than the rated voltage, this circuit is good, check the feedback circuit. Sometimes we have another fault. What is that? At that time the IC is switching at routine. When it is switching at routine, we are taking, we can say this is 12 volt, we are receiving 5 volt, 6 volt, but there is no fluctuation. This is stable, this is stable. What is the problem? The problem, this snubber circuit. If this snubber circuit, this diode is short circuit, what it will do, it will give a easiest path to this electrical current through the resistor. It will not allow to build full magnetic field in the primary. So that will cause to induce less voltage in the secondaries, so that it will receive a normal voltage. It will not build above than the over voltage protection limit. So IC will not go in reboot mode. At that time we need to check this circuit. Sometimes we have some bad soldering joints in the transformer, in the MOSFET, in the current sense resistor, high current components. If we have bad joint, the current will decrease due to increased resistance of the contacts. Desolder it and solder it again. If you have any other fault in your observation, if you have any other experience, please write in the comments. If you enjoyed this video, hit the like button. If you have any question, write in the comments. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.